So we are in the last section of today's lectures, brine mining. So what's the best way to manage the brine after you concentrate 50%? Do you have a 3.5% seawater concentration? Change to 7%. 7% of seawater salt. Currently, what we are doing is just to back ocean. Yeah. So initially, people are worried about what's the consequence of this high concentration to the ocean. Is there any problem for marine environment or ecosystem? And they investigated. It's a very well diffused in seawater. So it looks like not a significant environmental issue. So at this moment, most of these are measured just discharge back to the ocean. But this is kind of waste of overall salt management. So if we collect and produce this table salt, you have a lot of table salt. So how we produce table salt? Now, where do you table salt from? Yeah.
Depends where it's like huge deposit of like Canada has huge deposit of some.
Deposit of salt rock.
Yeah, sorry.
Salt rock. Yes, some of that, yes.
And some take the high wave of sea and just store that water, let it evaporate and
So in Australia, what's the most common brand of table salt? Nobody purchases the table salt. Yeah, this is every day you use, right? Table salt. But you don't know which one.
we know the color of
Have you ever heard of Sasa?
salsa.
Sasa, right? It's a red color. Yeah. Sasa. Sasa is the most effective our table salt. How we make this one is it's located in Queensland, and they just collect the seawater, evaporate with the sunlight. They keep accumulating your salt concentration, and salt will precipitate at 35%, 36%. When you have a 36% of salt, the sodium chloride creates your cubic crystal. So they collect your sea salt and put it in your bottle and just sell it. Yeah. So Sasa is the most common brand in Australia. How about the pink salt? So I'm sure that some of them, anybody utilizing pink salt? Pink salt. Yes, Malaysia, no, Himalayan salt, Himalaya pink salt. So Himalaya pink salt is from the salt line, the Himalaya area. So there are like a lot of pink color salt. The pink color is from iron. So they have iron every, yeah, like blood, your blood color iron. Combined with sea salt. Long ago it was the place of sea salt, and water is dry out. You just stay as a salt. So they change the rock, salt rock, with the iron. So pink color is from iron. So pink salt is was good for your body because they have a lot of pink salt. Even Australia, we have a salt rock in Western Australia. Because long ago, Australia was not the one continent. Half of them was ocean. So we have an ocean in the half of the plate, and then they change and combine. Then seawater was confined and they create the salt run. So if you go to the Western Australia, there are many, salt run underground. So you can collect the salt run. So table salt. If we can make a table salt from brine, 7%, and we can also possibly utilize also, right? Also, we have a critical mineral inside, so we can try to utilize this kind of salt and make a value of research recovery. So that's one of the, our target.
But it also has uranium and heavy metals.
And we're heavy metals. The seawater doesn't have heavy metal because heavy metal is very heavy. They have like three multivalent ions, three like some of the heavy atoms easily combined with the organic or some of the components. So heavy metal is easily settling down. So heavy metal can be detected on the sediment. So you have on the lake or even estuary, you have a lot of clay on the bottom sedimentation. Heavy metal is easily collected there because of their keep up in the lake heavy objects. Not in the seawater because they cannot travel to seawater because it's heavy. So it would be in the bottom of your water. So that's we can try to collect this kind of useful material, table salt. Or how about this construction? What's this material of construction? Concrete. Concrete. What's the compound of concrete? What's the element of what's the atoms? Elements. So you don't know. You're not civil engineer, right? I don't care what the concrete is. So your brain is not concrete enough.
Lime.
Something like that, lime, calcium,
Gypsum.
calcium hydroxide,
Silica.
calcium carbonate. So seawater contain, what's the concentration of calcium? 500 milligrams per liter. So if we collect calcium from seawater, we don't have to go like a calcium rock or some cement unit. They are mostly collecting this material from the mining side. So cement raw material is calcium hydroxide, calcium carbonate, seawater contain calcium, easily combined carbonate or hydroxide. So magnesium. Magnesium is very useful for minerals. Is water, in the mineral water, mostly they consider magnesium concentration because magnesium is good for our body. Cure some of the heart disease. So magnesium. So IBM, when they sell this drinking back to the water, they are trying to say that this is 1,000 years glacier melting back to the water from Alps and magnesium concentration happening from area. So they are trying to convince this is the historical trend of the area water, most expensive compared to other body water, right? Because people like to drink the Alps, glacier water, melted water, mineral water, magnesium. So that's what they are trying to brand their body water. But In fact, we are eating a lot of nomination, a lot of different sources. And it doesn't have to be reliant on the area, water. But that's how marketing, because you don't know water, what water, what's the best way to drink, what's not many people are there. Keep knowledge of water. So it's easy to convince people, oh, this is the natural resource. I've brushed your water, very clean, very mineral. So magnesium is also high concentration in seawater. So why not? We extract magnesium and try to mix with some magnesium. 1 kilogram is also $10 in the market price. So why not the magnesium? So there are many compounds we can utilize. So now we have operated seawater desalination for last more than 60 years. And they're getting more and more increasing number of the plants. The brine keep discharging, it's not really cost effective. And especially in the area of the Gulf and Land Sea, it's a little bit closed area. So if you keep discharging the brine, then you will accelerate the overall. Now it's already 4.5% compared to India Ocean, even Pacific Ocean, Atlantic Ocean. Concentration is already high. And they need more desalination plant, Land Sea, like Gulf area.
More energy intensive.
That's why it's a more energy intensive, also keep increasing the level of post concentration. So we need to think about different way to manage the brine. So now people are thinking about how to recover table salt, how to recover magnesium, how to recover calcium, how to recover something else. Well, that's how we can improve over our process. Same as long ago we never recycle wastewater. 30 years ago, 40 years ago, everywhere is water, everywhere is easy to drink without any problem. Now it's there are many different chemicals, there are many different contamination, there are many different viruses, there are many different pathogens, there are many different reasons people are afraid to drink this kind of So same to brine resource recovery. We need to think about how to recover something useful rather than just to go back and it's not the effective way to manage our brine. So let's talk about brine management. So this is what we are trying to achieve. Brine, seawater, there are many different elements. And this element can be one of the most effective compound we can recover. Sodium, potassium. So potassium is what utilization. So most of fertilizer, potassium is from seawater. So potassium could be a good fertilizer solution, yep.
Yeah.
And magnesium, even sodium chloride, calcium sulfate, and rubidium, lithium, vanadium, boron, gallium, molybdenum. So how we can treat after this brine? And we can separate with the multivalent ion and monovalent ion. The multivalent ion, monovalent ion. So we have technology nanofiltration. So we can separate sodium chloride, monovalent, and multivalent ion with sulfate, magnesium, vanadium, molybdenum. And after we separate, we have a different technology to collect the separation of different specific multiple ion, sodium, indium, vanadium, molybdenum, gallium. So this is possible to use the highly changeable selective membrane absorption ion in liquid. Also monovalent ion, rubidium, lithium, and sodium hydroxide. So sodium hydroxide is useful our alkali compound. So we can utilize this one for industry purpose to wash out the high caustic pigment. So we can separate monovalent ions, divalent ions, multivalent ions using different membrane technology, absorption technology, ionic liquid technology to have a selection. So what's the value? So you can see a lot of compounds there inside the seawater. So this is concentration in Gulf seawater. And this is the price in terms of kilogram. So let's see, $0.1, $1, $10, $110, $1,000, $10,000. So let's see the highest value. What's that? What's this? Rubidium chloride. $10,000 1 kilogram. If you collect rubidium in seawater, you need a very rich. Let's see, next step, lithium. $10 for 1 kilogram. And magnesium, bromide. So rubidium concentrate seawater is around 0.2 milligram per liter. Lithium is similar, 0.3, 0.4 milligram per liter. Bromine is a little bit better, 100 milligram per liter, bromide. And magnesium is high concentration, 1 gram per liter, 1,000 milligram per liter. This is produced 1 kilogram. So brine is double concentration. You have double concentration, and you can get higher concentration from the brine. It's only for seawater. We can make a good value out of it. Also, you know that the sodium chloride, we mentioned about table salt. It's around $0.2 1 kilogram. Yeah. So it's not bad. Yeah. So we produce a lot of sodium chloride without any problem, right? Even magnesium, calcium. We mentioned about concrete, calcium carbonate, calcium sulfate, calcium chloride, 0.1 to $0.8 per kilogram. So if you collect this kind of material from seawater, right, it's already double concentrated because we have a brine, yeah. So you can also have a good value out of this brine. So how we can challenge this one? Is it feasible or what's the best way to contribute this kind of resource recovery? So this is the already people are trying to recover resource from brine. So they want to use the brine resource recovery as well as the seawater desalination. So this process is different from what we discussed so far. We discussed it only for water production purpose. But this is the brine purpose and resource recovery. Because you produce your water, we have 1 kilometer tablet in Australia, $2.3. Yeah, 1 kilometer producing your seawater desalination 4 kilowatt hours. You spend a lot of money to produce water. So gap of this value is very small. But we need water. Water is very important. Yeah, our basic life requirements. So even though the gap of profit is not that high, but we have to invest. But when you consider resource recovery 1 kilogram, you have much more value from the resource recovery. For example, like a table salt. So you produce table salt after water extraction. If you convert table salt, sell $0.1, $0.2 for 1 kilogram, you already recover most of the investment than water production. So why not we utilize this kind of resource recovery rather than back to ocean? So this is they are trying with the Neo City in Saudi Arabia. It takes pure radioactive cartridges and they put nanofiltration to separate monovalent iron, multivalent iron, and goes through SWRO and PWRO, and the product produce the drinking water, and they have a collection of brine together with the nanofiltration material, monovalent, divalent, and goes to the distribution recovery setup, the membrane brine concentrator, crystalline, produce the sodium chloride 25% brine, which is the high value. Not because of stable salt, because of alkaline production of the NaOH, HCl. The sodium chloride is their main source of your acidic HCl and caustic NaOH for industrial application. So sodium chloride is not only about your table salt. You produce 2 million dry ton per year. When you produce 1 million per day of desalination. Also, you can produce table salt, crystal, also bromine, $10 per 1 kilogram. The concentration is good enough, so you can have a good bromine resource recovery from seawater brine. So that's they like to develop together from the Saudi Arabia NEOM project. So how we can achieve also different value out of it. So this is the US dollar for 1,000 kilometer, how much we can achieve from this kind of brine management. What's the value would be the best way, right? I mean, from seawater desalination. So the best value is sodium hydroxide. So 1,000 kilometer, almost 5,000. The sodium, there are many different concentration, seawater, and magnesium, almost $9,000. Yeah. And then HCl. So sodium hydroxide, HCl, can be produced from sodium chloride. It's not table salt. It's a high concentration of liquid condition. And then you can separate sodium hydroxide and HCl. This means you will get the more value using the sodium chloride, not only table salt, but also our NaOH, HCl production. Also aluminum chloride, 1,000, and potassium sulfate, hydrogen chloride, bromine, hydrogen carbonate, borate, and strontium, lithium, cesium, iron. So these are most potential material you can collect from the brine. So a lot of people target which kind of market price would be the best way to extract from our seawater brine. Also, you can see the potential revenue for the different magnesium sulfate and sodium chloride, also magnesium chloride, rubidium, and calcium sulfate, potassium chloride. So when you compare with the water, yeah. So if you just collect even this salt after brine, yeah, you already have much more value than just to water business from seawater desalination. And sodium chloride, bromine, magnesium, calcium salt would be the very high potential value. If you collect this one, so you can just give a free of water to the community. You don't have to charge the desalinated water cost because already they value magnesium, sodium, and rubidium have much more value than water cost, right? So that's how they like to implement. For example, like magnesium and concentration is almost 40% in seawater. So magnesium is a very high concentration, and this is the one of the distribution. 1, 2, 3, 4. It's like a cooking salt, potassium, magnesium, bromine. So this is they have a salt from this area mostly. So you can see the cooking salt everywhere, yeah, every continent, because it's easy to produce from seawater. And potassium, number 2. Potassium also they produce this area mainly. And number 3, magnesium. Magnesium also they have extracting from the conventional process. And number 4, bromine. Bromine, it's only very few area. This one, near the Dead Sea, because they have a more bromine concentration. the deadest concentration is almost more than brine concentration. Yeah, so they contain a lot of bromide concentration to produce the bromine. So this is the current. So we can utilize some of the multi sources to produce and recover the mineral in the world geographically. And this is the concentration and precipitate. So previously, we mentioned about calcium carbonate membrane fouling, right? But here is the resource recovery. The calcium carbonate 50 grams per liter. So when you have a high concentration of calcium carbonate, so concentration polarization attached on the membrane. So when you are in the outer membrane filtration, this is the fouling. But when you recover the 50 grams per liter, this is the resource for concrete. And calcium sulfate, sodium chloride, 100, but it's almost 360 grams per liter of concentration. You will precipitate also magnesium sulfate, potassium chloride, and magnesium chloride. So depending on your concentration, they are precipitate. So you know that what's the concentration in bulk one. You can slowly collect. In this concentration, you collect calcium carbonate, you collect the sodium chloride, you collect the potassium chloride, because they have a different solubility, right? So that's how we can easily separate different. So you can have from seawater, and you have a crystallization calcium carbonate. You will produce almost in the range of 50 grams per liter till 68%, and you will get the calcium sulfate, and 88% you evaporate. You will get sodium chloride and magnesium sulfate and magnesium chloride, magnesium, when you have a 99%, 98%, just evaporate. So you will collect. So that's how we can try. But table salt. So most of table salt we are eating it from evaporation method, right? This method. So what's the problem of this one? Not problem. So this table salt contains all the mineral inside, or there are many different salts available in the market. So some salts are from natural seawater. Some salts are mostly sodium chloride. Some salts are ionized salt, because our seawater salt in Australia, they don't have iodized what salt, so that they add a little bit of iodized, right? So we have this kind of extra salt. So sea salt, or just the sodium chloride, table salt. So when you produce the sodium chloride, they are targeting this level. Sodium chloride 88%. So still 12% liquid condition. So they discharge to the monovalent ion. Also, they discharge to the calcium carbonate or magnesium, some of the compound will be easily removed. So they specifically target sodium chloride in this condition. So which means while you are eating table salt, sodium chloride, even though this is produced from seawater, they already removed the other compounds, it's not all about. But when you say sea salt, what's the difference? Sea salt structure. If you see the sea salt structure, it's very much not regular type. But when you see the Sasa salt, they have like 1 millimeter of smaller, yeah, very consistent, your white color. Because they specifically target this 88% sodium chloride. But when you evaporate, you want to add it. They are all combined with sodium, magnesium, hydrogen, and other. So it's like the structure is very much irregular type. So which one is better to eat the salt? If you need more mineral, sea salt added without any, separation of this body sodium chloride. So they contain much more minerals inside because sea salt contain a lot of minerals. So that could be the best way. The problem is when you this is a very big, crystal. So crystals, your concentration also structure, even though they look like this great pipe, concentration is different. Some of them contain a little bit more this one, more this one. So it's like a very much different way of salt we are producing every day. And then if you like to have a more mineral, natural sea salt, the problem is that you cannot really handle this kind of salt. So that they are selling the purely sodium chloride precipitates at this stage. That's why it's very consistent. Also looks like very much favorable. Looking for the sodium chloride. So that's the precipitation we can utilize. Different technology, BWRF, WRO, and also distillation and crystallizers we can utilize. And this can be, otherwise you can use natural evaporation using sunlight, but this is very time consuming. Also, you need a very big lab. So if you want to use plant desalination, you have a limited space, and you have to utilize a lot of this kind of technology to produce your salt water. And also, this is the different summer membrane and solvent extraction, evaporation pond. Also, we can utilize this kind of process to recover different mineral sources. And they have some pros and energy consumption and how much it can be costed, and medium size, low size, very high size. Yeah, mostly summer process is a high or high step, and the medium size is membrane, and this low tech evaporation is low, so you can select which is useful for your resource recovery technology. And this is another, they like to develop as a resource recovery. So previously, New York City, they target specifically sodium chloride, liquid 25%, or table salt, crystal, and bromine. So three were main target compounds. But if you see this one, they are targeting on calcium carbonate and magnesium hydroxide, and they also target potassium chloride, lithium, and rubidium. So this is another process they like to develop. to produce the better quality of our research information. So that's how it can be managed, different resource. If you need more fertilizer, potassium would be best way to produce. Calcium carbonate could be a construction material, and magnesium has a high value. Lithium, rubidium, it's one of the annual process they like to develop this technology. So extraction of magnesium, relatively simple. So we have a seawater here and sunlight, magnesium chloride, hydroxide incorporate. The magnesium hydroxide will be precipitated. Then you put your acidic condition, produce the magnesium chloride. And this magnesium chloride, further, you can do some electrochemical process. The cathode, anode cathode, the chlorine can be produced from the chloride ion. Magnesium can be produced with the magnesium metal. The magnesium metal is more easy to transfer, easy to have a very high value than magnesium chloride. So you can also go through some of the electrochemical process to produce magnesium. How about bromide? The bromine concentration is almost 50 milligram per liter. The bromine, how we can extract? The Black Sea produce every day a lot of bromine, because inside the Black Sea water, they have a very high concentration of bromide, more than 200 milligram per liter. And once they put the chlorine, the bromide ion convert into bromine, the oxide, and then this bromine is more gas phase, so you can easily blow up, and you can produce the bromine liquid, very high purity. So where is bromine is used? Have you ever used bromine? No. Anybody? Have you ever heard about where is the bromine? Yeah. Because bromine market is almost 500 billion dollars every year. It's used for some replacement of the fluoride. So now people are talking about PFAS. And the fluoride compound is a very forever chemical. So how we can replace some of the material by the fluoride? The bromine is the same group. Fluoride, bromine. So they like to utilize the bromine rather than fluoride. And bromine can be used some of the fire retardant. The fluoride is used for fire retardant material. So when you have your extinguisher or fire station, all the white color is very much PFAS. Also, they utilize this one for bromine. And they have a lot of application. So bromine can be used this kind of application and easily separated from the gas liquid concentration. Rubidium is one of the important material in the medical, even space, GPS, and this is the good application for CT scan. So inside seawater, rubidium concentration is 0.2 milligram per liter. So if we collect, this is a high value for very high-tech application. Also lithium, rubidium, and this is a lithium. I don't have to talk about lithium because everybody knows lithium is very important. And then seawater also contain very high concentration of lithium. So you can see that how much value of lithium concentration in seawater is a huge amount. So you can see the lithium in ocean is 230 billion tons. And on land, we have a lithium mine in Australia, even Chile. Yeah. So 40 billion ton only land mine. So we can collect a lot of seawater lithium concentration and different absorption or electrochemical process selectively collect our lithium concentration from this technology. So this is the how it works absorption, like the ion exchange. So potassium, hydrogen, you can replace with lithium. So hydrogen ion can be replaced with the lithium and absorption, and you can have a desorption. So that's the how we produce. What's the performance from different absorbent? So what's the perspective for brine mining? What do you think? So that's your assignment. We want to know about your brine management idea in your report. So what's your best way to make your desalination design and brine management? So what kind of target you like to consider to include in your future brine perspective of our research report? So your assignment, another question is that how we can effectively manage this brine. I want to hear your own idea of design, which can possibly benefit to our community. Any questions from brine management? Do you feel this is the good way to go, or just too unrealistic, achieve a cost-effective brine resource recovery? What do you think?
Add little sugar, make a beer.
Sorry?
Add little sugar, make a beer.
Let's say again. What did you say? What did you say?
We will add little sugar to it and make a beer brand.
Okay, that's just okay. This is the tomorrow. We will continue from this one. So today, officially, everything ends. What time now?
Only half an hour left.
Half an hour. Okay, so we have a quiz time. So I have a 4 minutes for you. Yeah. So let's summarize today's lectures. Yeah. Can you come close? Or you don't go there? So we are just about to finalize. Last step, very important. Our quiz time. Please have a seat. Yeah, you don't have to bring everything. Please come here. Come close. So we have summarized today's lecture. So if you get the right answer, you will get your name. Yeah. So what's the quiz? What's the material of outer membrane? Active layer.
Polymer. It's a polymer.
Too broad.
Silicon.
Okay. It's polyamide layer, which is similar to nylon. And what's the osmotic pressure of our water?
28 bar.
Can you raise your hand first? Don't say, yeah. Okay, so this is the. Give me half. Give me some. Second. So, next question. What's the salt concentration in our bloodstream? One wait. 1%. Okay. Anybody there? 0.9. Huh? 0.9. 0.9. Very close. In fact, not substantial. 1% means 10 grams per liter. Even 0.9% is 9 grams per liter. So the right answer is 0.9 grams per liter. 0.9. So when you think about in your hospital, the saline water, yeah, so you just put the saline water to your body. So exactly 0.9, saline water inject your body because the body is very much similar concentration with 0.9. Otherwise, we have a problem. Saline water, 0.9 gram per liter, not percentage. Percentage is 10 grams. 1% is 10 grams per liter.
Yeah.
That's
That's the
completely wrong. But he didn't say unit, he said 1%, 0.9%, 0.9, he didn't say percent. That's why I just assumed
But
0.9
then
gram per
gram per liter.
Okay, next question. How many percent of seawater cover India?
80 to 70. 79%. 79%.
79. 75.
21% is land.
Maybe 50. Yeah, AI. So, what's the seawater cover in India? One percent. Who said 71%?
I 70. Close.
70.
No one is guessing. It's not very complicated.
71. Okay. He said percent. He said that even though. Okay. 71%. So we have coverage of, so you're getting close, but not quite right. So we have one more. No, don't give up. Don't give up. Don't give up. So you're close, but I did the right.
I'll ask Google first.
Last question. What's the water age of the earth? How old is this water in the earth? How old this water is in the earth? Yes.
Must
Now,
be
earth,
billion.
not the from.
Must be billion years.
Not quite. You have to say close. Yeah. 1.5 million.
Yeah, 4.5 billion.
1.5 million. Right.
Google, I Googled it.
I know. So better to find the Google rather than 1%. 70%. You're close, but now it's Hang it to the proper finally.
How old is Earth?
That's exactly the next question you can find out. Well. Okay, thank you very much, and looking forward to seeing you tomorrow at 11 a.m. Then we can go through the design. Okay, see you tomorrow. Thank you. Okay. Thank you.
The software is not running.
Software. नहीं रन ही नहीं हो रहा.
Yeah, we are not able to run this software.